Okay, so now you've heard me talk about the ideal gas, and I'm just going to quickly show you the difference between a real gas and an ideal gas. Now, even if you think about your everyday life, ideally there's certain things that you would like to happen in your life. Just getting to the right college, get 100% on the test. Ideally, these are all things that we want to happen. Right conditions exist for those to happen. But we know in reality those things don't always happen. So I'm going to show you the difference between an ideal gas and a real gas. And so here is the comparison. Ideal gases, we like to think of them as zero volume. However, we know in reality gases have a volume. Ideal gases, we pretend that there is no attractive forces between the molecule. However, we know that for the most part, attractive forces do exist. The molecules are attracted to each other, especially in a liquid state, they are more attracted to each other than in a gas, for example. Again, molecules move in perfectly straight lines in an ideal gas. Again, we know that this is not entirely true, that gases don't move in exactly straight lines. Okay, and again, the collisions are elastic and thus do not give up any energy. We know that that is not true. Collisions are not completely elastic. Okay, so that's the reality. We like to think when we are doing problems that we are dealing with an ideal gas, but at low pressures and high temperature, most gases will behave like an ideal gas. However, once that those two conditions, the pressure and the temperature decreases, the volume of the gas, when conditions favor a decrease in the volume of the gas, they cause the molecules to be closer together, so they're interacting more, they're colliding more, there's not straight lines, there's more attractive forces, so they're interacting more. These are no longer ideal gases, but instead they behave like real gases. So the ideal gas law takes into consideration the amount of molecules that you have. PV equals nRT. So we know that pressure, P stands for pressure. We know that V stands for volume in liters. T stands for temperature in Kelvin. N is for moles, the number of particles that you have in your gas. And P will be measured in kilopascals. Okay, so these are all ones you have to remember that this is going to be your units. Okay, and then you have a constant, 8.314 kilopascals times liter divided by moles times Kelvin. So this is its unit. You are given this. You do not have to memorize it. It is given to you. Okay. Note that nothing is changing when we use this formula. So read your question. If it's talking about the temperature at this point in time, and then they're asking for you for the temperature at the next point in time, you are not going to use the ideal gas law. However, if they're talking about a specific moment in time where they have the number of particles, the volume, the temperature, and they want to know the pressure, then you are going to use the ideal gas law. Okay, so remember, when it is talking about a change, you are not using the ideal gas law. But if it is asking for a specific moment in time, then you'll probably use the ideal gas law. And normally, if you see moles in the question, it's a dead giveaway. Okay, so let's take a look at an example question. You have 4 liters of ammonia gas in a container, and that container holds 2.17 moles at 206 kilopascal. What is the temperature inside the container? So again, here, it's not asking you about a change in temperature. It's just asking you what the temperature is inside the container at that moment in time. So it's the formula we need to use is PV equals nRT. We have our number of moles, we have our pressure, we have our volume, we don't have our temperature, they're asking for that, and we have our constant, 8.314. PV equals nRT. We are isolating T, so divide this side by nRT, that side by nRT. Substitute, we get our values. These cancel out, liter cancels out, mole cancels out, and we're left with Kelvin. So 45.7 Kelvin. Example number 2, 6.55 moles of oxygen gas in a container. It's held at 200 Kelvin and 152 kilopascals. What must the volume be? Again, PV equals nRT. Substitute in our values. We're looking for the volume. We're going to isolate volume. And you should get liters, because mole cancels out mole, Kelvin and Kelvin cancel out, and kilopascal or kilopascal cancel out, so you're left with liters. 71.7 liters. Now we're not quite done these, so you have PV equal nRT. So you can have now a whole mix of questions, given particles, then figure out your ideal gas law. All right, so make sure you fill this sheet out before you come to class tomorrow as well. What are chemical reactions used in mining? Smelting. Metal smelting process, use of metals, useful metals such as zinc, lead, copper, and nickel. Smelting, it can be harmful because they're releasing elements like cadmium, arsenic, and sulfur dioxide and mercury all into the air. It can impact the air quality because the oxides will form acids in the atmosphere and then cause acid rain. And people with respiratory illnesses normally are greatly impacted by these factors in their area. Okay, so Sudbury is another is a smelting town for nickel. Government regulations have improved the air quality and reversal of acidification of local waterways. Okay, we're going to work on worksheet 7.